Hi, my name is Silvana Aristizabal, and this is my lab report for Lab 5, the Falling Slinky. Here's the table of contents of what we're going through in this presentation. Firstly, the introduction. The overall purpose of this assignment is to observe, analyze, and model the motion of the bottom of a falling slinky using video and computational tools. Then we will compare observed position from video analysis with the predicted position from the computational model. We will achieve this using three main tools: Tracker for video analysis, CloseScript for building the computational model, and spreadsheets for graphing the observed position of the object from the video analysis to compare with the computed data. In this experiment, the system is the slinky itself, while the surroundings include the earth, air, and any external contact. All of this helps us gain a deeper understanding of the bigger picture behind Newton's second law of motion, drag force, and other forces that influence the motion of the bottom of the slinky. So let's explore more about these principles. So, the momentum principle states that the net force acting on an object is equal to the rate of change of its momentum over time. In other words, when a force is applied to an object, it doesn't just change its velocity, it changes its momentum, which is the product of its mass and velocity. We can see here how by deriving from the momentum principle, we can obtain the velocity update formula. This formula allows us to determine the object's velocity at each timestamp when dealing with a non-constant force. Once we have the updated velocity, we can use it in the position update formula to predict the object's future position over time. This principle helps us understand why objects speed up, slow down, or change direction depending on the forces acting on them. Then the drag force is a resistive force caused by the air opposing the motion of an object. It increases with speed and depends on shape, surface area, and air density. In this experiment, it acts upward of the falling slinky, opposing gravity and the motion of the slinky coils, and it affects how quickly the bottom of the slinky accelerates and reaches the terminal velocity. Now that we understand this, let's see our procedure. So we first use Tracker to analyze the motion of the bottom of a slinky that is let go from a specific height. Then, based on the position, velocity, and time gathered from the video analysis, we created a computational model of the slinky's bottom position on CloseScript. Then we graph the position versus time results from both the computational model and the video analysis, and we compare results and understand the difference between the data and discuss findings. Now let's take a look at the actual motion we analyzed. Here's the video of the slinky being released, which we use for our video tracking by examining its motion frame by frame. At each of the red diamonds, we collected the position data. When we graph the white data over time in spreadsheets, this is the graph we got showing the time of where the bottom of the slinky did not move and then its progressive falling. With the data collected, we were then able to construct a computational model of the motion we observed. So to build a computational model, we first started by creating the two graphs we wanted to analyze, one with no air resistance and the other one with air resistance. Then we stated all of the constants we will be using for this computational model. We stated the initial stretch positions. The top initial stretch position is the height of the man holding the slinky. Then we decided to add a delay time for when the bottom starts moving, so the model was more accurate. Here in the no air resistance model, we first started by calculating the spring force, then the net force on the top and the bottom of the slinky. Then we used Newton's second law to update velocity and update position for the top part of the slinky. And then for the bottom part of the slinky, we used the delay time and then Newton's second law to update velocity and update position. And lastly, we updated time. For the air resistance model, the only difference between this code and the no air resistance model is that we had to add this force here when calculating the net force on the top of the bottom, which accounts for air resistance. And this is our final code. So for our results of the code, we got here the bottom of a slinky with no air resistance. We can see how the bottom follows a somewhat constant pattern, while the with air resistance follows a non-constant with the deviations, which we think correlates with the first graph we built with the tracker data. So some possible errors that could have affected our results are human error when conducting video analysis, rounding errors, camera misalignment, and dismissing other external environmental factors. So now to reflect on the overall experience, we can answer these questions. So does the bottom of the slinky of your model stay stationary just like in the video? So in my final computational model, yes, but this is because I included a variable to represent a moment in the tracker video when the bottom of the slinky begins to move. This allowed the model to be a better match for the behavior seen in the real footage. In my first model, this wasn't the case. I assumed that the slinky started falling immediately, which caused the position graph to show a continuous negative slope, which does not accurately reflect how the bottom remains still at first. And here are some of the general conclusions. So tension force within the slinky stretches between coils. Initially, this upward force counteracts gravity at the bottom, keeping it suspended until the upper coils collapse downward. Then drag force opposes the motion of the slinky through the air. While small compared to gravity and tension, it becomes more significant as the slinky speeds up and affects the overall flight dynamics. Then, the interaction of this force, especially how tension temporarily cancels out gravity at the bottom, explains the delayed motion observed in both the video and the improved computational model. Thank you.